Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is electromagnetic interaction. Our objective is to discuss several important interactions between magnetism, electricity, and movement that govern the fundamental working principles of rotational electrical machines like motors and generators. We'll additionally explain the origin of counter-electromotive force, or CEMF, experienced by motors in operation, and counter-torque, or braking, experienced by generators in operation. Before we begin, a brief housekeeping note. First, let it be known that this lecture series uses conventional current, where conventional current is defined as flowing from the positive terminal of a source through a load and returning to the negative terminal of the source. I will not use electron flow. If you want to use electron flow theory, that's fine, but these diagrams won't work. Next, I need you to put your 3D glasses on because we're going to be talking about electromagnetic interactions in three-dimensional space. It may be difficult to visualize 3D interaction on a 2D screen. However, I'm going to do my best to draw these interactions carefully and accurately. You may have to pause the lecture to fully comprehend a diagram, and I'm encouraging you to do so. Related to 3 dimensions, here's some ground rules about the illustrations utilized in this lecture. If I have to draw something on a flat screen where something is shooting out of the screen at your face, like an oncoming arrow, you'll see the point of the arrow coming towards you. This isn't exactly the most desirable perspective of a moving arrow. If, however, something is moving into the screen, you'll see the fletchings of the arrow moving away from you, as if you're trying to embed the arrow into a peaceful forest-dwelling mammal. Finally, I'm going to consistently use 3 colors to describe the 3 phenomena we're dealing with. Conventional current is blue and flows from positive to negative. Lines of magnetic force are gray, and they travel from north to south poles in free space outside of the magnet. Finally, movement is green, and the arrow indicates the direction or applied force. All right, I believe we've set ourselves up for success, and if everyone's in agreement, let's dive right into our planned discussion of electromagnetic interaction. As you are no doubt aware, motors convert electrical power into rotating mechanical power. Generators, in contrast, convert rotating mechanical power to electrical power. One might think these roles are mutually exclusive. However, as we'll soon learn, there are intriguing dualities between motors and generators. Long story short, electricity, magnetism, and movement are related phenomenon. As an extremely superficial summary, the interaction of 2 properties results in the third. Motors move because of the interaction of electricity and magnetism. Similarly, generators produce electricity because of the interaction of movement and magnetism. If we're thinking on a more holistic level, motors and generators might be better considered 2 different aspects of what might be better thought of as a rotating electrical machine. Before we reach this level, we first need to introduce a couple basic electromagnetic interactions, specifically the right-hand rule in electromagnets, Faraday's law of electromagnetic induction, Fleming's left-hand motor rule, and Fleming's right-hand generator rule. It is an observable fact that as conventional current moves through space, it creates a magnetic field around it. The polarity of the resultant magnetic field can be predicted by holding the right hand in a loosely held hitchhiker pose with the outstretched thumb pointed in the direction of conventional current flow. The curling fingers indicate the polarity of the revolving magnetic field north to south. You'll note that current flow in one direction creates a given magnetic polarity orientation, whereas current flow in the opposite direction creates a magnetic field of opposite orientation. The right hand can be used to determine the polarity of the magnetic field in 3-dimensional space. Consider the cross-section of a conductor with conventional current entering the screen as indicated by the fletchings of the arrow entering the screen. Point your right thumb into the screen and notice which direction your right fingers curl. Unless you've got an odd-shaped right hand, you should notice the resultant magnetic field turning clockwise. Consider another current-carrying wire with conventional current leaving the screen, as indicated by the point of the arrow leaving the screen. Point your right thumb out of the screen, i.e. towards your face, and notice which direction your right fingers curl. Unless you've got an odd-shaped right hand, you should notice the resultant magnetic field turning counterclockwise. Now, rather than think of these 2 current-carrying conductors as separate unrelated entities, think of them as a cross-section of a current-carrying loop of wire in 3-dimensional space. Current comes into the loop on the left and out of the loop on the right. As a result, the field on the left rotates clockwise, and the field on the right rotates counterclockwise. Notice how the 2 magnetic fields mutually reinforce each other at the center. Recall that magnetic lines of force outside a magnet leave a north pole and enter a south. Thus, a north pole is established at the bottom and a south pole is established at the top. We've in effect turned this loop of wire into an electromagnet. Anytime current flows in this loop, we have a functional electromagnet. The advantage of electromagnets, in contrast to permanent magnets, is that the resultant magnetic field can be turned off. If current flow stops, the magnet stops, minus a tiny amount of residual magnetism. In addition to being energized or de-energized at will, the polarity and strength of this resultant electromagnet can also be controlled. If current flow through the loop changed direction, such that current entered to the right and came out on the left, an application of the right-hand rule on the left side demonstrates the left section's magnetic field turns counterclockwise, and the right section's magnetic field revolves clockwise. As previously, the two magnetic fields mutually reinforce each other in the center of the loop, only this time a north pole is established at the top and a south pole is established at the bottom. Related to this phenomenon, the strength of the resultant magnetic field can be changed by varying the amount of current flow. In short, less current flow means less magnetism, and more current flow means more magnetism. Up to a certain point. We'll discuss saturation in later lectures. In summary, a loop of current carrying wire will create an electromagnet, and the strength and polarity of the resultant magnetic field is capable of being controlled by altering the direction and magnitude of current flow through the loop. Lastly, unlike a permanent magnet, one can turn an electromagnet off by halting current flow. Motor and generator windings don't consist of single loops of wire, but rather numerous loops in close proximity. Consider the two-dimensional cross-section of a three-dimensional helical coil of wire, such that conventional current enters the right-hand side of the coil and leaves the left. An application of the right-hand rule demonstrates the right side of the coil's magnetic field turns clockwise, and the left section of the coil's magnetic field turns counterclockwise. As with a single loop, the magnetic fields mutually enforce each other through the center of the helical coil, such that all lines of magnetic force in the center of the coil leave the top, i.e. establish a north pole, and all lines of the magnetic force in the center of the coil enter the bottom, i.e. establish a south pole. Here I've illustrated these as separate magnetic fields, but that's not really what happens. The numerous magnetic fields actually coalesce such that the larger coil of wire establishes a single magnetic field of unified polarity, with the north in the top and the south in the bottom. The larger number of mutually reinforcing loops in the coil simply establish a stronger magnetic field than would a single loop of wire. Here's a practical demonstration of these previous concepts. Consider a coil of wire covered with a thin resin insulator wrapped around an iron nail. The iron nail is electrically isolated from the wire. However, the permeability of the iron concentrates the lines of magnetic force better than would free space. With no current traveling through the wire, no magnetism is observed. The moment current starts flowing in the coil, magnetism is observed. When current flow stops, the magnet stops. It should be noted that one could also selectively wind a coil such that two equal and opposing magnetic fields are created in close proximity, such that they cancel each other out. For our purposes, an electromagnet coil is wound such that the fields mutually reinforce each other, such that a unified electromagnet is formed. The take-home points about electromagnets are this. The polarity of a resultant magnetic field in a coil of wire is dependent upon the direction of current flow. The strength of the resultant magnetic field is dependent upon the magnitude of current flow and the number of loops in the coil. Lastly, you can turn an electromagnet off by halting current flow. Let's now examine Faraday's law of electromagnetic induction, which states a voltage will be induced across the terminals of a wire proportional to the number of turns in the wire and the rate of change of the magnetic field. I say again, a voltage will be induced across the terminals of a wire proportional to the number of turns in the wire and the rate of change of the magnetic field. Note the emphasized phrase, rate of change. This implies it is not necessarily the strength of the magnetic field, but rather the rapidity with which the magnetic field changes that influences the resultant voltage generated. Slowly changing magnetism results in lower induced voltage, whereas rapidly changing magnetism results in higher induced voltage. Prime movers, i.e. the wind, water, expanding steam, or engine turning a generator, need to turn it at a sufficient speed for a usable voltage to be generated. There's a couple ways to create a changing magnetic field. First, one could have a constant magnetic field, either a permanent magnet or an electromagnet with a fixed level of current traveling through it, mounted at a stationary point, and then one could rapidly pull, push, or spin a coil of wire in close proximity. The faster the coil was pulled, pushed, or turned by a prime mover through the stationary magnetic field, the greater the rate of change of the magnetic field and the higher the voltage that would be generated across the terminals of the coil. 2. One could reverse this and keep the coil stationary, and then have a prime mover rapidly pull, push, or spin a magnet in close proximity. The faster the magnet was pulled, pushed, or turned, the greater the rate of change of the magnetic field and the higher the voltage that would be generated across the terminals of the coil. One or both of these principles together are exploited in the traditional generation process, where some prime mover uses some physical force to move a magnet in close proximity to a coil, or vice versa. The faster the relative movement of the magnetic field, and the more turns in the coil, the more voltage will be generated across the terminals of the coil. As an alternate method, one could also forego the process of physical movement altogether and employ changing current, as is commonly available in AC systems. Consider two stationary coils in close physical proximity. If current through one coil started sinusoidally oscillating back and forth, the associated magnetic field in the first coil would expand and contract as a function of current magnitude and direction. The second coil, being in close proximity, would experience a changing magnetic field and thus experience an induced voltage where the faster the rate of change of current in the first coil and the more loops on the second coil, the higher the voltage that would be generated across the terminals of the second coil. This is the principle employed by transformers, electrical devices we'll examine at length in later lectures. Thus far, we've been considering the observed effects across an open coil with no load. What if the coil, with some induced voltage, was incorporated in a circuit, including a load? Follow this chain of logic carefully. Given a voltage is induced across the terminals of the coil, and the coil is part of a circuit including a load, current should flow in the closed circuit. Given our earlier understanding of electromagnets, we could surmise that this new flowing current will create its own magnetic field. This new magnetic field will interact with the original magnetic field, and we can use this interaction to our benefit, such as making a motor convert electrical input into mechanical output, making a generator convert mechanical input to electrical output, or making a transformer step up or step down voltage without physical contact. Which leads us right into our next topic, motor and generator action. These actions can be respectively illustrated using Fleming's left-hand motor rule and Fleming's right-hand generator rule. Let's first examine motor action using our previous understanding of current flow and the associated magnetic field. The basis of a lot of motor action is that misaligned magnetic fields exert a force as they seek alignment. Norths attract souths and repel other norths, as do souths attract norths and repel other souths. Opposites attract and like repels. This explains the close bond between you and your lazy lab partner. Consider the two-dimensional cross-section of a three-dimensional loop of current-carrying wire, where conventional current enters the screen on the right and leaves the screen on the left. Our previous understanding of current magnetism demonstrates the magnetic field rotates counterclockwise on the left and clockwise on the right, such that the mutually reinforcing magnetic fields establish a north pole at the top and a south pole at the bottom. If we place this electromagnet in close proximity to another magnetic field, we'd expect them to interact. Consider what happens when we place this electromagnet inside another permanent magnetic field, oriented such that the lines of magnetism travel north to south, left to right. Given like poles repel and opposites attract, we might expect the electromagnet to be torqued clockwise as the two magnetic fields seek alignment. Let's explore the origin of this phenomenon. Note the magnetic field on the top of the left-hand conductor is opposing, whereas the magnetic field on the bottom of the left-hand conductor is aiding. These magnetic fields coalesce such that there are more lines of magnetic force on the bottom and less on the top. Unified magnetic field below the conductor acts to push the left-hand conductor upwards. Similarly, note the magnetic field on the top of the right-hand conductor is aiding, whereas the magnetic field on the bottom of the right-hand conductor is opposing. These fields coalesce so that there are less lines of magnetic force on the bottom and more on the top. The unified magnetic field on the top acts to push the right-hand conductor downwards. Given the left and right conductors are in fact cross-sections of the same three-dimensional coil, this coil will be torqued clockwise as the magnetic fields seek alignment. While it is entirely possible to explain this interaction using our previous understanding of current magnetism, it can be more succinctly explained using Fleming's left-hand motor rule, which uses the open and outstretched left hand to illustrate how a current-carrying wire and a magnetic field feels a resultant force. Extended fingers of the open left hand are oriented to the magnetic polarity, pointing north to south. The open palm is oriented such that conventional current leaves the palm. Magnetism and electricity interact to create movement. This is motor action. The outstretched thumb indicates the induced direction of movement. The left-hand motor rule applied to the left conductor demonstrates that the left conductor would be forced upwards. By all means, pause the lecture and use your left hand to confirm this. Similarly, the left-hand motor rule applied to the right conductor demonstrates the right conductor would be forced downwards. Again, by all means, pause the lecture and use your left hand to confirm this. The result being that this electromagnet would be turned clockwise as the magnetic fields seek alignment. This is the source of motor action. Electricity and magnetism are the causes, and movement is the effect. Motors use the interaction of magnetism and electricity to generate movement. Before we continue, I'd like to provide an opportunity to practice the application of Fleming's left-hand motor rule to the following 3 additional scenarios, where the original scenario appears in the upper left-hand corner. For the second scenario in the upper right-hand corner, consider the same external magnetic field, only this time current in the electromagnet has a reverse direction, entering on the left and leaving the right. For the third scenario in the lower left-hand corner, the external magnetic field is oriented north to south, right to left, and current in the electromagnet enters on the right and leaves the left. And finally, for the fourth scenario in the lower right-hand corner, the external magnetic field is oriented north to south, right to left, and current enters the electromagnet on the left and leaves it on the right. See if you can apply Fleming's left-hand motor rule to all these scenarios and try to determine in which direction the two-dimensional cross-section of the three-dimensional loop will be turned. By all means, pause the lecture and try this yourself. If you're tracking, you should have observed the following scenario. For the second scenario, an application of the left-hand motor rule for the left conductor demonstrates it would be forced downward, whereas the one on the right would be forced upward. This current-carrying loop would therefore be torqued counterclockwise as the electromagnet seeks alignment with the external magnetic field. For the third scenario, an application of the left-hand motor rule demonstrates the left conductor will be forced downward and the right one will be forced upward, such that the loop will be torqued counterclockwise as the magnetic field seeks alignment with the external magnetic field. Lastly, for the fourth scenario, an application of the left-hand motor rule for the left-hand conductor demonstrates it will be forced upward and the right one will be forced down. The loop of wire will therefore be torqued clockwise as the magnetic field seeks alignment with the external magnetic field. The observant among you might be drawing this conclusion. In order to swap the direction of rotation, one can change either the orientation of the magnetic field or the direction of current flow, but not both. We'll examine how this phenomenon is put to use in controlling the direction of DC motors in later lectures. Now that we've got a good understanding how magnetism and electricity create movement in motors, let's now examine how movement and magnetism create electricity in generators. This is really an application of our previous understanding of Faraday's law of electromagnetic induction, where a voltage will be induced across the terminals of a coil proportional to the rate of change of magnetism and the number of turns in the coil. Fleming's right-hand generator rule is simply a way to determine the polarity and direction of these results. Fleming's right-hand generator rule uses the open and outstretched right hand, where the thumb indicates the direction of movement and the extended fingers indicate the magnetic lines of force north to south. These are the generator's inputs: magnetism and movement. The output, electricity, is an arrow shooting straight out of the palm, where the direction of the arrow indicates the direction of conventional current flow established by the resultant induced voltage polarity. Since we've had some practice with these types of problems already, let's apply Fleming's right-hand generator rule to a couple example scenarios. Consider a conductor moving through a magnetic field, oriented such that the lines of magnetism travel north to south, left to right. This conductor is moving upwards through the magnetic field. Orient the outstretched fingers of your right hand such that the fingers point north to south. Orient the right thumb such that it points upwards in the direction of movement. Unless you got a weird-shaped right hand, your right palm should be flat on the screen. This implies that voltage will be induced such that conventional current will flow into the screen. This is generator action. Generators use the interaction of magnetism and movement to create electricity. You note in this example, we pushed the conductor upwards through a stationary magnetic field. What if we did something different and kept the conductor stationary and instead pulled the magnetic field downwards? Would anything change? Not in the slightest. Keeping the conductor stationary and moving the magnetic field down is the exact same thing as moving a conductor upwards through a stationary magnetic field. All that matters is there exists relative movement between them, and a change in magnetism exists such that a voltage is induced in the conductor. Relative movement is the key. In fact, both the magnetic field and the conductor could be moving in the same direction. As long as they move at different speeds, there will be a change. As an example, asynchronous generators, a subject we'll examine at length in later lectures, have a rotating magnetic field in the stator, and the rotor is rotating at another speed. As long as the rotor exceeds the speed of the stator, there's relative movement and generation can unfold. Just so you can get some practice with Fleming's right-hand generator rule before I blow your mind with some other content, here's a couple example scenarios. By all means, pause the lecture and use Fleming's right-hand generator rule to determine the direction of induced conventional current given the indicated direction of the magnetic field and the movement exhibited. If you're tracking, you should have observed the following results. For the first scenario, the magnetic field is oriented north to south, left to right, and the conductor is being pushed downwards through it. Orient the outstretched fingers of the right hand so that the fingers point north to south. Orient the thumb such that it points downwards in the direction of movement. Unless you got a weird-shaped right hand, your right palm should be facing you. This implies that voltage will be induced such that conventional current will flow out of the screen. The second scenario is admittedly a little odd. The magnetic field is oriented north to south, top to bottom, but it's not stationary. It's being moved rightwards at some speed. The conductor is also not stationary. It's also moving rightwards, only at a slower speed. This ultimately results in the magnetic field catching up and passing the conductor. When it does so, it's almost like the conductor was standing still and the magnetic field moved rightwards. Alternatively, this would be equivalent to keeping the magnetic field stationary and moving the conductor left. Either scenario results in relative movement between the conductor and the magnetic field. Orient the outstretched fingers of the right hand such that the right hand fingers point north to south, top to bottom. Orient the right thumb such that it points in the direction of movement. Unless you got a weird-shaped right hand, your right palm should be facing you, albeit at an odd angle in your wrist. This implies that voltage will be induced such that conventional current will flow out of the screen. As I mentioned previously, this type of relative movement between a moving magnetic field and a moving conductor is also employed in squirrel cage induction motors, where a rotating magnetic field in the stator would move faster than the conductive bars in the rotor, such that current flows on the rotor without the need of physical contact or electrical connection. We'll examine squirrel cage induction motors and asynchronous generators in later lectures. Alright, now that we've got an understanding of electromagnets, Faraday's law of electromagnetic induction, Fleming's left-hand motor rule, and Fleming's right-hand generator rule, you should be at a point where you can confidently explain motor movement and generator action on an introductory level. Let's take it one step further and examine the origins of two additional phenomena: counter-electromotive force, or CEMF, observed in motors, and counter-torque, or braking, observed in generators. Both of these phenomena can be thought of as an innate opposition or resistance to the effect that originally induced it. As an example of this unfolding in real life, politely ask your lazy lab partner to show up on time and prepared for class. You can be damn sure they're going to show up later, drunker, and dirtier than usual because they innately oppose your efforts to make them a functional member of society. There's a natural tendency for things to want to remain where they are, and if you want to affect some change, you got to put in some additional work. Let's examine counter-electromotive force first. As you are no doubt aware, the interaction of magnetism and electricity create movement. This is motor action as defined by Fleming's left-hand motor rule. My question to you is this: why does a motor winding with an at-rest resistance of, let's say, 20 ohms only draw 2 amps when operated at its rated speed when energized by a 120-volt source? An application of Ohm's law demonstrates a motor winding with an at-rest resistance of 20 ohms would ordinarily draw 6 amps when energized by a 120-volt source. This doesn't happen, but rather the motor draws, let's say, only 2 amps of current when energized by a 120-volt source. This seems a little odd, but it's an example of what can and does happen when motors operate at their rated speed. The answer is CEMF. Allow me to explain. CEMF is an oppositional voltage generated in a motor winding that opposes or is counter to the applied voltage and keeps current at a manageable level when the motor is in operation. One way to think of CEMF is as an imaginary series opposing source counter to the external source driving the motor. In our example, if we were to assume the motor winding remained at 20 ohms of resistance, which it doesn't because there's other components including inductive elements that I'm neglecting right now. A CEMF of 80 volts in opposition to the externally applied 120 volts would result in a 40 volt differential across the 20 ohm winding, thus explaining why the motor only draws 2 amps while in operation. You note CEMF is a variable quantity dependent upon speed of the motor. At rest or 0 RPM, CEMF is 0 volts and the source experiences no opposition, thus explaining inrush, a sudden surge of current when a motor is initially started. Whereas at the rated speed, let's say 1750 RPM, the CEMF rises to 80 volts and the motor draws only 2 amps. The easiest way to explain CEMF is this: motor first, generator second. Motor first. Consider a conductor in a magnetic field oriented north to south, left to right. Conventional current travels into the wire. An application of Fleming's left-hand motor rule demonstrates the conductor would be forced downwards. This is motor action. Now keep your left hand on the screen. Generator second. This is now a conductor moving through a magnetic field. Overlay your right hand on the left such that the right hand fingers point north to south. Orient the right thumb such that it points downward in the direction of movement. Unless you've got weird shaped hands, your left and right hands should be back to back such that the left hand palm points into the screen and the right palm points out. This is CEMF. The secondary generator action produced as a consequence of motor action opposes the initiating effect, in this case current. Now get your hands off the screen. Everybody in the room is looking at you funny. Let's do the same thing for counter torque or braking experienced by generators. The prime movers that drive generators need to exert a measurable amount of force against an oppositional torque to produce electrical power output. And counter to a lot of incorrect thinking, prime movers don't just free spin in space. On a basic level, one can think of counter torque or braking as the effort necessary to move something through a magnetic field. It can be explained using similar techniques we use to explain CEMF observed in motors. The easiest way to explain counter torque or braking experienced by generators is this: generator first, motor second. Generator first. Consider a conductor moving upwards through a magnetic field oriented north to south, left to right. An application of Fleming's right-hand generator rule demonstrates that conventional current travels into the screen. This is generator action. Now keep your right hand on the screen. Motor second. This is now a current-carrying conductor inside a magnetic field. Overlay your left hand on the right such that the left-hand fingers point north to south and the palm matches the direction of conventional current flow into the screen. Unless you got weird-shaped hands, your left and right thumbs should be pointing in opposite directions. The right thumb up and the left thumb down. The secondary motor action produced as a consequence of generator action opposes the initiating effect, in this case movement. This is the counter torque or braking or oppositional drag a prime mover has to overcome to produce electrical power. Electrical power doesn't magically appear out of thin air, but rather a generator consumes the mechanical power in the form of torque and rotational speed from some other phenomenon and converts it to electrical power output. For both CEMF and counter torque, it's important to remember and differentiate between cause and effect. A motor initiates movement because of current and magnetism. CEMF is secondary because induced movement interacts with existing magnetism to oppose initiating current. Similarly, a generator induces current because of movement and magnetism. Counter torque is secondary because induced current interacts with existing magnetism to oppose initiating movement. Long story short, CEMF and counter torque mean the real world opposes your efforts to change it, and if you want the world to change, you got to put in the work. Alright, I believe we accomplished what we intended to do in this lecture and more. In conclusion, this lecture examined fundamental interactions between magnetism, electricity, and movement for rotating electrical machines, motors, and generators. We introduced and discussed electromagnets, Faraday's law of electromagnetic induction, Fleming's left-hand motor rule, and Fleming's right-hand generator rule. Additionally, we discussed counter-electromotive force, or CEMF, experienced by motors, and counter-torque, or braking, experienced by generators. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.